Hello and welcome back to this course. So we were looking at the ohmic laws, wherein we saw that this voltage that is basically invested, that is an energy invested in basically bringing the charge from one end to the other end of the conductor, and this is again limited by the ohmic resistance of that particular conductor. So we write this as an eta, that is because that is an ohmic over potential energy that we invest, and that is equal to I times R ohmic. And this R ohmic is predominantly sum of the electrical resistances of the individual cell components. For example, it can be the sum of the resistances offered from the electrodes or the bipolar plates or the current collectors together, plus the ionic resistance, in other words the resistance offered by the electrolyte to basically transfer these protons from one side to the other. So that is what we have written, and if we see that this R ohmic, which is sum of the electrical resistance and the ionic resistance, among these two, ionic resistance of the electrolyte, that is the resistance offered by the electrolyte to transfer protons from one side to the other, is far more than the individual electrical resistances and their sums, as because the main constraint is from the proton transfer. So let us go ahead and we write. So we have already written this R ionic is far greater than R electrical, and if we neglect electrical resistances, so if we neglect electrical resistance, which is the electrical resistance of individual cell components, we can say that R ohmic is almost equal to R ionic, which is equal to L by sigma times A, where L is the thickness. So let me draw that. So if you have this cell, let us say this is the electrolyte and this is the electrode. So this is the area of the electrode, let us call this as A. So from this is how from this area the protons will be transferring normal to this area and will be getting onto the oxygen side in case of hydrogen oxygen fuel cell. So if this is the electrolyte, this has got ionic conductivity sigma. So this is ionic conductivity, and this is the thickness, or in other words this is the L, that is the distance travelled by protons from one electrode to the other. So L stands for the thickness of the electrolyte. So this is basically thickness of the electrolyte, which can also be assumed to be the distance to be travelled by protons, or it can also be said that it is a distance between the electrodes. The anode and cathode. So as we can see, this R ionic is directly proportional to the length, or that is the thickness of the electrolyte. So if the thickness of the electrolyte, that is L in our case, increases, R ionic, or we can also in some extent we can say R ohmic, will also increase linearly. So it has got a very linear relation as the L increases or the thickness of the electrolyte increases, and the reason is because if the thickness of the electrolyte increases, protons have to travel more distance in order to reach the cathode from anode, and in other words they have to invest more energy to bring the protons from anode to cathode. So that dV by dx, which we have seen earlier, that is the potential gradient has to be increased if the protons have to travel more distance, or in other words the ohmic over potential will be more if the thickness of the electrolyte is more. So, we can understand this concept in a simplified version. For example, if you want to travel from point A to point B, right. So, if this distance increases, obviously we are expected to burn more fuel and reach the destination. So, as the distance increases, as we can write, as the distance increases, the energy, in other words the fuel that we put in the vehicle, energy invested in the fuel in the vehicle will also increase, right. So, that is why we have to see that the thickness of the electrolyte is as minimum as possible, so that we do not invest in terms of more ohmic over potential and we can save in terms of energy. So, let us solve some examples. So, let me take one cell having area 1 centimeter square, the other cell is this is A2, let us call this as A1 and this is A2 as 10 centimeter square. The resistance is total resistance, this is 0.1 ohm, total resistance of the second cell is around 0.02 ohm, and both of these cells, let me write, both of the cells are drawing current at the rate. So, current density is given 1 amps per centimeter square. Okay. So, we need to find, so you have to evaluate the eta ohmic for both the cells. Okay, this is the problem that we have been given. So, let us find out the ohmic resistances or ohmic over potentials. For that, let us first find out the area specific resistances. So, let us find out area specific of cell 1 and 2. Okay. So, RASR 1. So, as we know, RASR 1 is the total resistance multiplied by the total area of that cell. So, R1 into A1, R1 we have been given, it is 0.1 ohm and area is 1 centimeter square. So, area specific resistance for the first cell will be 0.1 ohm centimeter square. And what is the area specific resistance of the second cell? It is again a resistance, the complete resistance of the second cell multiplied by the total area of the second cell. So, it is 0.02 times 10. So, it is 0.2 ohm centimeter square. So, now let us find out the ohmic over potentials. So, we know eta ohmic is basically current density times area specific resistance. So, ohmic over potential for the first cell is basically current density times area specific resistance of the first cell. So, current density is 1 amps per centimeter square. Let me write the unit here in the bracket, 1 amps per centimeter square into the area specific resistance of the first cell was 0.1 amps, 0.1 ohm centimeter square. So, if we connect that, this becomes 0.1. So, centimeter square gets cancelled, it is basically into ohm, which is volt. So, that is we get ohmic over potential for the first cell as 0.1 volt, and what is the ohmic over potential for the second cell, it is J times R ASR 2. So, current density is same. What gets changed in case of second cell is the area specific resistance, which is 0.2 ohm centimeter square. So, this comes 0.2 volt, right. So, what does it imply? It implies that, or let me try it in other words. So, if you look at the ohmic over potentials of the first and second cell, despite having total resistance lower compared to the first cell, the second cell is expected to have more over potential. In other words, we will be losing more energy while drawing the same amount of current despite having the lower resistance. The reason is because the area is increased. As the area is increased, the area specific resistance will also increase, and that is why we will get more ohmic over potential. So, let me write that one. So, despite having total resistance, which was given in the numerical, total resistance that is lower than the first cell, second cell will lose potential. So, when we say we lose potential means our potential is more, we lose more potential more than the first cell for same current density drawn. And why is it so? Since RASR of the second cell is greater than the RAS of the first cell. Let us solve another example. So, let us take two fuel cells. So, this is fuel cell 1 and fuel cell 2. Fuel cell 1 is using electrolyte as Nafion 212. Nafion 212 means the first two digit signify the molecular weight of that polymer, and the last digit 2 signifies the thickness of that electrolyte. So, 2 stands for 2 mil. So, 2 mil means the thickness is roughly 50 microns. Area is, let us say, 25 centimeter square, and conductivity of this electrolyte is typically 0.1 Siemens per centimeter. Let's keep most of the things same, that is area and the conductivities. Let's change the electrolyte. So, now in the second cell is using electrolyte as Nafion 211. So, it is 1 mil. So, thickness will be around 25 microns. Let us keep the area same. Since it is the same polymer that is being used in both of the electrolytes, the conductivity will also be same. So, what we have here is, this is the area, this is 25 centimeter square, thickness is, this is L, which is 50 microns, and conductivity is 0.1 Siemens per centimeter. So, let us first find out the total resistance of this cell. R equals L by sigma A. So, it is L is 50 microns, that becomes 0.005 centimeter. Sigma is 0.1 Siemens per centimeter. So, let me write unit as well. So this is centimeter and area is 25 centimeter square. So as you can see, the centimeter square gets cancelled and we get total resistance in ohm. So it is 0.002 ohm. This in first case. What is the case with the second cell? So let's calculate R2, L by sigma A. So L is half of the first one. In first case we were having thickness of 50 microns. In second cell it's around 25 microns. So it is 0.0025 centimeter. Conductivity and the thickness, conductivity and the areas are same. So the resistance will be exactly half of that compared to the first cell. So as you can see, if we keep the if we reduce the thickness of the electrolyte, as we discussed this before as well, the resistance will be decreased, and if the resistance decreases, we can expect more protons to travel from anode to cathode, and we will expect better results from that particular cell. So let me write. So as the thickness of the electrolyte increases, so area specific resistance, that is RASR, which is L by L over sigma, will also increase, I would say, linearly. So to reduce the resistance, that is R, we should, in other words, we should use thinner membrane or electrolyte or, in other words, I would say the distance between the electrodes, that is anode and cathode, should be as minimum as possible. But where does it lead to? So what are the consequences? In other words, what are the consequences of using a thinner electrolyte? So if, let me say, however, if the thickness of the electrolyte is reduced, what happens? First case is we will be exposed to more fuel crossover. So more fuel crossover will take place. We have discussed this before. Let me quickly go through this one more time. So what happens is, if we have a very thinner electrolyte, or let me draw it in a 2D way. So this is the anode and cathode. So if this thickness, which is L in our case, is reduced so marginally or so much that this hydrogen, instead of getting oxidized at the catalyst layer, which is here, this is our catalyst layer. So instead of getting oxidized here, so we know H2 gives 2H plus 2 moles of electrons. So, this is the oxidation which is supposed to take place at the anode side, which is the catalyst layer of the anode. And so, hydrogen gets diffused as a molecule. So, right, and it reaches the cathode and there it gets oxidized. So, this is the fuel crossover. So, let me write this up. So, hydrogen instead of getting oxidized at anode, it basically flows through the electrolyte or through those small micropores. It flows, or I should say leaks, through the small micropores of the electrolyte, and then gets oxidized at cathode, which is highly unfavorable in our case because we do not want our hydrogen to get oxidized at the cathode side. We want it to get oxidized on anode side so that we can get the electrons in the external circuit, and the whole purpose of having a fuel cell in reality will then be served. So, if you want these electrons to reach the external circuit, we have to have this hydrogen getting oxidized at the anode side. So, we have to sort of choose the electrolyte thickness such that the fuel crossover is also minimum, and the resistance offered to proton transfer is also not very much. So, there is a trade off between fuel crossover and the proton transfer. This is with respect to the first consequence of having less thickness of the electrolyte. What is the other consequence if we have thinner electrolyte? So, mechanical integrity, mechanical strength or the integrity will also be decreased substantially, and since we are dealing with a thinner electrolyte, there is a possibility of uneven thicknesses as well, and the uneven thickness of the electrolyte will lead to the hot spots and subsequently the failure. So, what do we mean by uneven thickness? So, if the thickness, if we take an example of Nafion 212, which is typically 50 micron thick, so we can expect marginally uniform thickness across the electrode. So, it could be 40, 46, it can be 50, there can be 52 or 48. So, on an average the average thickness is 50 microns. However, if we choose an electrolyte which is very thin, let us say 10 microns, so then we cannot expect to have a uniform thickness of the electrolyte across all the length and width. So, here it could be 7 microns, it could be 5 microns, it can be 10 microns, here it can be 11, can be 8 microns or so. So, average, despite having average thickness, let us say 10 microns. So, since we have a very small thickness here at one of the locations, for example, this one, let me highlight this. So, here, so this is the location where the thickness is very small compared to the average thickness. So, thickness is very small compared to average thickness. And where does it lead to? So, since we have a very small thickness here, so while they, and as we know, the protons are generated at the catalyst layers at the respective sites. So, where we have a lower thickness, we can expect the hot spots to be made available. So, this site particularly is prone to hot spots. So, this site is prone to hot spot. Hot spots in very simple term means that the temperature of the electrolyte or this membrane in this case will be much higher compared to the rest of the temperatures across the length and width. So, for example, this electrolyte temperature is around 65 degrees Celsius. We may expect to have temperature of around 80 degrees or even higher at this particular hotspot, and this will ultimately lead to failure because we are generating hotspots at different locations, and that will decrease the mechanical strength of the electrolyte at that particular location, and eventually the cell will fail. So, this is the case with respect to the having thinner electrolyte. What is the other consequence? So, if you have a thinner electrolyte, electrical shorting will also take place. So, let me write this electrical shorting. So, very thin electrolyte will also lead to electrical shorting. In other words, so if the thickness of the electrolyte is very small, like we discussed in the last example, if the thickness is roughly 10 microns or even lower, in other words, the anode and cathode are very closely placed across this electrolyte. So, we have a higher probability of electrical shorting in between these two electrodes, and if such phenomena happens, if the electrical shorting takes place, we will not be able to get any electrons in the external circuit, and the very purpose of having fuel cell in the picture will not be served, and that is why thin electrolytes are typically not preferred, or they are avoided primarily because of these 4 reasons. So, we will take on with the resistances and how they are added in the electrical circuit in the upcoming sessions. I will stop here. Thank you.